Can you can you all hear me now?
Yeah.
All right, cool. So what I want to do now is start the next unit. And so whatever I discuss now will not be on Friday's exam. And we're going to focus on chapter 29, which is on magnetism. So this first chapter in the unit is really on the fundamentals of magnetism. The next chapter is on really sources of magnetic fields, how you calculate them. Well, I got to be careful. My emphasis will be on how to calculate them. There's also a section on magnetic materials, which I generally don't have time to discuss. I'll say a little bit about it today, but it's probably worthwhile for you to read through the section on what makes materials magnets. Okay, I'll say a little bit about it. Like I said, I'll say a little bit about it here today. And then the last chapter in the unit, chapter 31, will focus on magnetic fields that vary with time. And those generate electric fields. And so that's where the interesting applications come in. Okay? So to me, I think the last chapter in this unit is one of the most interesting ones in this course. So today I want to start by saying some things about the magnetic field. The magnetic field is a little bit more difficult to talk about, and it's because magnetism is really a manifestation of relativity. Of course, for many years, folks understood about magnetism. But it wasn't really until relativity that really understood it better. So I want to say a few things about magnetism before we start delving into the subject. And here's some applications of magnetism. These notes are a little bit old because some of the things up on there, one of the things on there is kind of old. Motors, you're going to be building a motor this semester. Loudspeakers, testing for fingerprints, MRI. Scientists call it NMR, but NMR means nuclear magnetic resonance. Okay. The compass, magnetic tape. In the old days, when you recorded things, it was on magnetic tape. The mass spectrometer. If you've had chemistry, you've probably talked about the mass spectrometer. And cyclotron. And there's a lot of other applications. And I'm going to skip this video. There's something missing there. I don't want to play those videos because I have copyright issues. Magnetism had been known for many years. About 2,000 years ago, folks have discovered that the lodestone attracts iron. That lodestone magnetizes iron. Like poles repel and unlike poles attract. Okay. Around 1269, the field lines on a spherical magnet, it was discovered that the field lines on a spherical magnet meet, they form lines like the meridian lines on a sphere. And all magnets have north and south poles. This is around 1269. And eventually it was discovered that magnetism was due to either moving charge in a wire or moving electrons in a material. And it was discovered that the force between the poles of a magnet depends on 1/r squared. But I want to show you why magnetism really is a manifestation of electricity, of relativity. Suppose I have a current-carrying wire. And there's a great video of this online. In fact, I put it in your modules for this unit. There's some great videos in the modules. So let's say we have wire carrying current. Of course, if you have current carrying wire, the positive charges, I know they're stationary. And the electrons are the ones that are moving. So let's say the electrons are moving this way. Okay, which means if the electrons are moving this way, the current is in the opposite direction. So if you look at it, on average, I mean, these things are just drifting. These electrons are just drifting to the right. And this is really not a good picture because really what the electrons are doing are bouncing back and forth off the atoms, off the nuclei of the atoms in the material. But on average, what you'll see is an equal number of positive charges and negative charges. The density of positive charges will be equal to the density of negative charges in a wire in general. So if I have a positively charged particle here, just sitting there, really since this has no net charge on average, this thing is not going to experience a force. Is everyone okay with that? On average, if I put a positive charge here, this charge is not going to experience a force because the net charge at any time in this wire is 0. The net positive charge and the net negative charge, or the charge densities, they're about equal. So this thing is not going to experience any force with the current running through a wire. Does that make sense? Now,
Yeah.
let's let the charge move to the right with the same speed as the drift velocity of the electron. We're assuming this is constant. So let's let the charge go to the right at the same speed. Now, according to us, you say, well, this is still, it's neutral. So this thing is not going to experience any force. Okay. But what about if I'm in the reference frame of this positively charged particle? What do I observe? According to relativity, what happens to the distance between these positive charges? I see these positive charges go by me. What happens to the distance between them according to relativity?
They drift apart.
Not apart, right? Because there's length contraction, right? Objects that move by you, the distance decreases, right? The distance between the ends decreases. For let's say a ruler, the distance between the end of the ruler decreases. The ruler gets shorter.
Oh, right. Yeah.
So these get closer and closer together. Now, the electrons...
I was thinking you meant the charge and the positive charges, so yeah.
I'm sorry?
I thought you were saying the charge itself versus the positive charges. I was thinking the opposite, or same.
I'm just looking at the distance between them.
Yeah.
So the distance between them gets less, right?
Mm-hmm.
What about the distance between the electrons? Because you're not moving with the electrons. Before, the electrons were moving by you. What happens to the distance between the electrons? You're moving with them.
Do they just stay the same then?
Well, originally they were, when you were stationary, they were moving by you, right? So now you're moving with them. And so you're not going to observe any length contraction, correct?
So they would just stay, they would look like they're not moving, right?
They will look like they're not moving, but they will be further apart.
Oh, okay.
So what's going to happen is you're going to have a much higher positive charge density than negative charge density. Really, the overall effect is you're going to see this thing is going to see more positive charge than negative charge. And what's going to happen? If this sees a positive charge above it, what's going to happen?
When it repel it?
It'll repel it. So this thing is going to want to go down. So if I'm in a reference frame of the positive charge, I'm going to see this thing move downward. I'm going to see it experience a force. But if I'm observing it from a stationary frame, I see this positive charge go by me, I say there's no force on it. There's something wrong with that. How can you have this charged particle experience a force in one reference frame, but not in another reference frame? That violates the principle of relativity, because the laws of physics are the same in all reference frames. If you experience a force in one frame, you have to experience a force in the other frame. Does that make sense?
Yeah.
Now, I am ignoring something. I have ignored something. Okay, because earlier I said, if I'm standing here watching this charged particle go by, this thing is neutral. On average, it's not going to experience a force. But this thing that's moving relative to me does experience a force. It experiences a force due to the magnetic field in the wire. If a wire carries current, then it behaves like a magnet. Current carrying wires actually will behave like a magnet. And so now you have this charged particle moving in the vicinity of the magnetic field, and if you do the calculation, you will find that this charged particle will actually get deflected downward. So the force on this object in my reference frame is due to a magnetic field. The downward force on this object in its own reference frame is due to an electric field. It shows you how the electric and magnetic field are intertwined. Okay? And you have to have the electric field. The electric field is a manifestation of relativity. Without, you can't, if there was, you could not reconcile this problem without the existence of relativity. Basically, magnetic fields are due to relative motion, because in the frame of the charged particle, these positive charges are stationary. And so the force it experiences is due to an electric field. But to my reference frame that I'm watching this thing go by me, the force on it is due to a magnetic field. So when you see magnets working, when you run a current through a wire and it acts like a magnet, you are actually observing a manifestation of relativity. It's a demonstration of relativity. These magnets, these permanent magnets, what makes something magnetic? It has to do with the motion of the electrons in the atoms. Now, I don't want to get into all the details because it's a little bit involved. Every electron acts like a magnet. It has an intrinsic magnetic field due to something called its spin. There's also a magnetic field due to the motion of the electrons in an atom. But the main contribution to the fact that these bars are magnetic are due to what's called the spin of the magnet. That's a purely quantum effect. And it doesn't come up naturally. If you try to solve the equations which govern the atoms, there's something called a Schroedinger equation. the concept of the idea of spin doesn't come out of that. But if you solve the relativistic version of that equation, spin comes out of that. And it is the spin of the electron that are in this material that mainly cause this material to be magnetic, to act like a magnet. So that's why I say magnetism really is a manifestation of relativity. Okay, so even though we knew about magnetism for a long time, it really wasn't until around until after Einstein came by that we saw that, oh, this is a manifestation of relativity. And in fact, Einstein's paper that came out with, you know, the E equals mc squared equation that came out was a paper on electricity and magnetism. That's why I'm covering relativity in this course. The only problem is I don't have the time to show you the relativistic relationship, the details of the relativistic relationship between the electric and magnetic fields at a relativistic level. That I don't have time for, and it does get complicated. Okay, so let's talk a little bit about magnets. We can understand magnetic fields with field lines. So what I'm going to do now is just state some facts regarding magnets. If you take a compass, okay, and you can use it to map out the magnetic field lines. Let's say you take a bar magnet and a compass. And let's say this is the south pole of the magnet, this is the north pole of the magnet. And I want to basically map out the field lines. I take a compass and I can map out the field lines. They look like this. This is the north pole of the compass, the south pole of the compass, the north pole of the compass, the south pole, okay? And so the compass will align such that its north pole aligns towards the south pole of the magnet. The field lines do this. They form closed loops. Okay. Magnetic field lines form closed loops. Electric field lines do not form closed loops. Okay. The magnetic field lines circulate, and they go from the north pole to the south pole. And you can see that with a compass. So that's the big difference between the electric field and magnetic fields, that they form closed loops. They close upon themselves. Here are the magnetic field lines due to a current-carrying loop of wire. Actually, let me do this for you guys so you can see it better. Here are the magnetic field lines, the yellow lines, due to a current-carrying loop of wire. They form closed loops. And the direction of the field at any point in space is tangent to the field line. Where is the magnetic field strongest?
Is it in the middle?
In the middle, because the field lines are bunched, right?
Yeah.
So that idea still holds true, that the density of field lines is indicative of the strength of the field. Here are the field lines due to two closely spaced magnets. And if you notice in the middle, the field lines are pretty uniform. The Earth is also a magnet. All right. Here's a picture of the Earth, and if you can see in the middle, I drew a bar magnet. That's really how the Earth behaves. And there you see a compass whose plane is tangent to the surface of the Earth at that location. Look at can you see the north and the south pole of that magnet in that picture?
Yeah, their south is at the top, or is where the North Pole would be.
That's right. The south pole of the Earth's magnetic field is near the Earth's North Pole.
But they're not in the same spot, right? They're slightly different.
Yeah, they're off a little bit.
Because I know that if you go magnetic north, you don't reach the North Pole.
And so there's an angle. So if you take a compass and you try to point it north, right? You try to point it north. It's really not going to point true north because of the Earth's magnetic field. In fact, it depends that the angle between the direction the compass points north and true north changes as you move on different points on the Earth. In fact, the angle between true north and your compass north can be as much as 90 degrees, depending on how much iron is underneath you. The angle between the north pole of the magnet and true north is called a declination angle. Okay?
It's called what, Harry?
And that angle varies depending on where you are on Earth. Depends on how much iron is underneath you. Now, regarding the Earth's magnetic field, there's strong evidence suggests that the Earth's magnetic field is dependent on the Earth's rate of rotation. And it has been, it's been hypothesized that the Earth's magnetic field is due to convection currents. And these are motion of charges or motion of charged ions or electrons that are circulating inside the liquid within the Earth. The large deposits that we have of iron inside the Earth, they're molten since the temperature is high. And really, because the temperature is high, it's hard to get a permanent magnet from the iron. And so only near the Earth's surface will the iron have an effect locally on the magnetic field. That's why when you move around, the angle between true north and the compass's north varies. Questions on that?
So the angle varies based on how much iron is near you?
Yeah, in your location.
Okay.
So that angle could be off, your compass could be off by 90 degrees. So you need to take that into account when you're using a compass. So you can see how the compass can lead you astray depending on the composition of the Earth beneath you. Now there's another angle. So we talked about the declination angle. There's another angle called a dip angle. I have this little magnet. I don't know if you can see it. It's on a universal joint. It can rotate in any direction. And you can kind of see that the red part points downward. So when I hold this object tangent to the plane of the Earth, the magnet points downward. The angle the magnet makes with the horizontal is called a dip angle. So it has a component of magnetic field that goes downward. Okay, there's a component of the Earth's magnetic field that points towards the Earth. And you can determine that the angle with with basically a magnet that's mounted on a universal joint. Let's call it a dip angle. Of course, to do this, you got to make sure you're in a region where there's not a lot of magnets around. There's a lot of magnets right now in this room. So this might not be accurate. Okay. I think the dip angle in Sacramento is around 38 degrees below the horizontal. And by the way, regarding the Earth's north and south pole, it's been known to flip, right? The magnetic field of the Earth has been known to flip. This magnetic field is not very high. It's not a big magnetic field, it's small, but it does have effect on the electrons. In fact, when you come to do the oscilloscope quiz, when you work on this, what you can do is all you got to do, because this works with electrons going through it. The Earth's magnetic field affects the electrons. So basically, if you just have a trace, just ground this, you put this thing on ground, so you just get a horizontal line, and you just reorient the oscilloscope, you will see the trace change directions. Because the electrons are affected by the Earth's magnetic field. And we'll talk about the strength of the Earth's magnetic field a little bit later when we introduce the units for the magnetic field. Now remember that we talked about the electric flux, and the electric flux was a quantity that's proportional to the number of field lines penetrating through a surface. We can define something called a magnetic flux too. The magnetic flux is the integral of the magnetic field, or the integral of the perpendicular component of the magnetic field over an area. And the unit for the magnetic flux is the Weber, or Tesla meter squared. So the question is, since the electric field lines begin and terminate on negative charges, and the electric field lines extend to infinity, the electric flux through a closed surface is proportional to a charge. What about for magnetic fields? Well, the magnetic field lines form closed loops. The number of field lines entering a closed surface equals the number of field lines leaving the closed surface because they form closed loops. The magnetic flux through a closed surface is zero. So the magnetic flux through any surface that I choose, because they form closed loops, that's my surface, is zero because the number going in equals the number going out. The magnetic flux through a closed surface is zero. Isolated magnetic charges don't exist. All magnets come in dipoles. All magnets come with a north pole and a south pole. So if you take the integral of the magnetic field over a closed surface, it's always zero. There's no such thing as a monopole, okay? There's no such thing as a monopole. It's different from the electric field. That's the big difference, okay? So this is really Gauss's law for magnetism. It's very easy. That integral is zero. Isolated, and this tells you isolated magnetic charges do not exist. If you take a magnet, you break it in half, that magnet, well, those two magnets will have a north and a south pole. all magnets come in dipoles. People have been for years trying to isolate one of the poles. They haven't succeeded yet. Of course, if they once they do, then this equation has to change. By the way, Gauss's law for the electric field and Gauss's law for the magnetic field form two of Maxwell's equations. Oh, what causes the magnetic field to flip? That's a hard question. I mean, that's a hard question to answer. I'm not sure if the geologists know the answer to the question. I mean, because it's hypothesized that the magnetic field is due to the motion of charges in the at the center of the Earth. So I couldn't answer. I'm not sure what causes it to flip. I don't even. I don't know. I don't have an answer for you. That's a good question. What causes and what causes the flip? And I don't think they have a clear answer. Mainly because we don't have a clear answer as to what causes the Earth's magnetic field. But that's a good question to ask the geologist or the geophysicist. Sorry, I don't have an answer to that. Maybe I'll try looking it up, but I don't think there's an answer to that question. At least not right now.
No worries.
So, suppose a magnet designer tells you that he or she can produce a magnetic field given by that expression over all space. Is this person telling you the truth, or is this person lying to you? I will say this, if you know Calc 3, if you understood the divergence theorem, the answer to this question would come really very easily to you. But I actually have to do it the long way. So Gauss's law for magnetism says that the integral of B dot n dA equals 0. So if that's the case, if I get 0 for this box, then we're okay. The person's telling the truth. If I don't get 0, then the person's lying to me. So let me draw my box.
Professor,
Yeah.
why do we use B for magnetic field?
Yeah.
Is M already used?
Well, M is used for magnetization.
Oh.
There's a vector called magnetization. Actually, B is the magnetic field in a vacuum. There's another one where you multiply B by what's called a permeability, and they would call that H.
Okay.
Yeah, I don't remember the historical.
I was just curious,
Yeah.
just because we use kind of random letters sometimes, it seems. So.
Well, like for momentum, right? You use P for momentum.
Yeah. Or rho for density.
Yeah, I'm not sure where that came about. I mean, we use theta for angles a lot of times too, right? But yeah, I'm not sure. I guess a question of historical content, I guess. Let me redraw the picture so it looks more like okay. So I'm going to draw the y-axis. I'm going to use a weird coordinate system. This is the z-axis. This is still a right-handed coordinate system. Okay, so the magnetic field points, the magnetic field B is equal to B naught x over A I hat. And I got to calculate the flux through each surface. I want to see if this is 0. Okay, this box is dimensions of A by A by A. Okay. So let me draw some normals to the surfaces. And top and bottom. And this is in the j hat direction. This is in the minus j hat direction. And right and left and front and back. So this is in the minus k hat direction. And this is in the okay, because I got to take the dot product of this field with all these unit vectors. What is the dot product of this field with this vector? You have two vectors that are perpendicular to each other. What's the dot product equal to? So the dot product again is for physics, you have to remember this. You have to remember it as well as you know how to add. Okay, that's the equation for taking the dot product. So what's the dot product of two vectors that are 90 degrees apart?
And a 0?
0. So when you consider the top surface and the bottom surface, they will not contribute to the integral. Okay, so B dotted with n top equals B dotted with n bottom equals B dotted with n front equals B dotted with n back equals 0, because the vectors are perpendicular to each other. These are the only ones that give you non-zero contribution, because the dot product is not going to be 0 because the two vectors are either parallel or anti-parallel to each other. Let's do B dotted with n left. It's going to be B naught x over A I hat dotted with negative I hat. What's I dot negative I?
Is it negative 1?
Negative 1. But what is x on the left surface?
A.
No, on the left surface.
Oh, it's 0.
0.
So it becomes 0, right?
Yeah.
So overall.
So this is equal to 0. So the only term that contributes is going to be B dotted with n right, which is going to be B naught x over A I hat dotted with I hat. But x equals A on the right side, right?
Yeah. Isn't it technically B naught times x over? Oh.
Yeah, so you get B naught. So now I want to take the integral The only term in the dot product is this. And so the area, I can take this out of the integral because B naught is constant. And so this is the area of this surface, and that's going to give me B naught times A squared. Is that equal to 0? No,
No.
these are not 0, right? This is the dimensions of the box. This is a constant, it's not 0. And so the person who told you that they created a magnetic field that has this value everywhere in space is lying to you. Okay? This integral is not 0, and so they're lying to you. There's a section in chapter 30, which I added to your reading assignment for this chapter. This is actually covered in chapter 30. It's one section. But I like covering it here because it's related to the field. And yeah, I apologize. I should have said we use B for the magnetic field earlier. And so I'm going to a lot of times say for the magnetic field, I'm going to write down, instead of writing out magnetic field.
Wait, Professor, why is it A squared? Why wouldn't it just be A?
Because it's an area, right?
Oh, it's the area. That's right.
Right, dA.
Yeah. Yeah.
Okay. So just to show you, I mean, you know, if you want, actually, if you, have you folks had Calc 3?
I have.
A better way to write it is this. You wouldn't have to do all this work. So if you could calculate the divergence of the magnetic field, you could tell right away that that magnetic field is not possible. Okay. Now let's talk about the force on a charge in a magnetic field. We can derive this equation. I was going to state it from experiments. If you look at the force on a charge, now that we know a little bit about the magnetic field, we know a little bit about magnetic field lines, let's talk about the force on a charge in a magnetic field. If the particle's not moving, okay, so if particle won't experience a force. All right? So the charge in a magnetic field has to be moving in order for it to experience a force. Furthermore, the velocity of particle must have a component of V perpendicular to the magnetic field. If the velocity is parallel to the magnetic field, it will not experience a force. Okay? So in order for a charged particle to experience a force in the magnetic field, it must be moving and it must have a component of its velocity perpendicular to the magnetic field. Actually, let me see if I can demonstrate that. Let's see if I can demonstrate that. You see that tube? And I got to be careful because I don't want to electrocute myself. Oh, I got to plug it in. Do you see the green light in the tube? Or is that too hard to see?
I might be seeing it.
Hold on, let me magnify it some. You know, I have only one set of lights in here. I mean, one switch, so I can't turn off some of the lights. Can you see the beam? Let's see. Can you see it moving?
Yeah, it's right in the middle, right?
Yeah.
Oh, yeah.
Okay. So, what is that green light that you see? Well, you have electrons going from, you're going from left to right. Okay. Electrons are going from left to right. How do you know? How do we know the electrons are going from left to right? There's a gas in there. The electrons are colliding with the gas molecules. The gas molecules go into an excited energy state during the collision, and when the gas molecules go back to original state, they give off light. It's green. So that green light is indicative of the path of the electrons that you see. And so if I can move the electrons, then the green light will change directions too, because you're exciting different atoms. If I take this magnet, and I don't want to get too close because I don't want to get electrocuted, if I bring this from the side so that the magnetic field is parallel to the velocity vector, nothing happens. Now watch when I go perpendicular. Can you see the beam deflecting?
A little bit, yeah.
Let me turn the lights off. Well, it's going to be kind of dark.
Don't electrocute yourself.
Yeah. I can see a little bit.
Oh, yeah, there it is.
You see the beam deflecting?
Mm-hmm.
Okay. So, but the hard part is when I try to put it parallel, because I'm going to be close to one of those leads. But if you go parallel, the beam won't move at all. If I go to the top, the beam has to come out of the screen, and I don't think it's going to happen. It's going to come towards you guys. It still moves a little bit up and down because it has a component this way. Okay, let me turn this off. Okay, let me go back to where we were at. So, the velocity of the particle must have a component of v perpendicular to b. Furthermore, the force, if you do an experiment, the force is perpendicular to the velocity vector and perpendicular to b, a magnetic field. Okay, the resulting force, I don't know if you noticed that the beam was going this way. My magnetic field was either pointed towards you or towards me, and the beam either moved up or down.
Yeah.
That's because the force is perpendicular to both v and b. That's always true. Okay? Oops. I don't want to show this video. I'm not going to run the video for this.
This cathode ray tube injects a beam of electrons into a
Sorry, I'm trying not to run the video. just because of copyright. Okay, so the force on a charge in a magnetic field, because it has this behavior, involves a cross product. I don't know if you've noticed that if F is perpendicular to both V and B, that means that you have to deal with the cross product. The force on a charged particle in a magnetic field is proportional to Q, and it depends on the cross product between V and B. You folks remember the cross product?
Yeah.
Okay, so, and you know that the cross product is a way to find a vector that's perpendicular to two other vectors. That's really what a cross product is. And so F sub B, the force on a charged particle in a magnetic field is perpendicular to both V and B. And in fact, if you have a charged particle in an electric and magnetic field, then the total force is Q times Z plus Q V cross B. So this is the total force. And this is called a Lorentz force. Okay, that's called a Lorentz force. But we're going to focus on this for now. Okay, the force on a charged particle in a magnetic field. The total force is just our old Q times Z plus this one. So, by the way, this equation plus 4 Maxwell's equations summarizes this whole course. So at the end of the semester, I'm going to summarize the whole course, show you the 4 equations plus this one is all that's needed to be able to do problems. Okay? So we're building towards that. Let's look at the case where E is 0 and just look at the magnetic force. And again, I'm writing this down. This is based on experiment. We're not deriving it. We know from experience that F is proportional to Q, or the magnitude of F is proportional to Q, it's proportional to V, and proportional to B. And the angle between V and B. So the magnitude of the force, using our definition for a cross product, is the magnitude of Q times the magnitude of V times the magnitude of B times the sine of theta, where theta is the angle between vector V and vector B. If we solve this for B, then this is the force, which we can measure, over Q, V, sine of theta. So this is how we can define the unit for the magnetic field. It's the force divided by QV sine of theta. And if you look at it, it's a Newton divided by a Coulomb meter per second, which is a Newton over amp meter. And this is a Tesla. Like the car, right? That's the unit, the SI unit of the magnetic field is the Tesla, and is defined by this equation. 1 Tesla, there's also another unit, is a 10,000 Gauss. The Earth's magnetic field, just to give you some perspective, is half a Gauss. Okay? Ballpark figure, of course that depends on where you are on the surface of the Earth, but the ballpark figure of the Earth's magnetic field is about half a Gauss. It's not a very large field. A Tesla is a very large unit for a magnetic field. A 1 Tesla field is strong. If you look at the magnets that are used for your MRI, there are a couple Tesla. Okay, you're not supposed to wear any you're not supposed to have any magnetic materials when you get a MRI, right? That's a strong magnetic field, like 2-3 Tesla. And you can go online and find videos of objects in very large magnetic fields. Some materials have various properties where you can actually suspend them in the magnetic field. Like I've seen videos of fruits being suspended in a magnetic field, even a frog.
What's the is it a capital T for Tesla?
Capital T, yeah.
Okay.
Yeah, good point. It's a capital T for Tesla.
And also, I'm assuming Tesla, that kind of Tesla, is that similar to where like Tesla coils come from?
Yeah, Tesla. That's right. From the Tesla coil. Tesla was a genius.
Yeah.
He didn't get enough credit for what he did during his lifetime.
Yeah.
So this cross product, of course, if you want to calculate the cross product, you remember how to calculate the cross product, well, you have to set a determinant. You got to do this. And if you don't remember how to do the cross product, back to chapter 11 of your textbook, which discusses how to do the cross product. Okay, but so this is how you would evaluate it in general. Okay, and you have maybe 1 or 2 homework problems where you actually have to go through and evaluate it this way. But most of the problems we do, V is perpendicular to B, for example. For most of the problems that we do, V is perpendicular to B. I mean, this angle is 90 degrees. And so trying to work out that determinant for the case where theta is 90 is kind of cumbersome. And so there's another way to figure out the direction of the force on a charged particle in a magnetic field when this angle's 90 degrees. Okay, and we use the right-hand rule. Do you remember the right-hand rule in 205 in your first course?
Yeah, I think so.
Okay, so if I have...
Oh, yeah. Sorry, I'm learning a different right-hand rule in my statics class, so that's why I was... With the 3 fingers, right? That right-hand rule?
Yeah, and
Okay.
everybody does it, because I was taught differently. What works for you, you just use what works for you. If you remember the one with the 3 fingers, that's fine. Yeah, you form your right hand, I gotta use the wrong hand. You form your right-handed coordinate system, right?
Yeah.
Okay, so if we have, let's say, a charged particle moving to the right with velocity b. I'm going to draw a coordinate system. I'm going to draw a 3D coordinate system. Let's say the magnetic field points out of the board. Okay? And I'll show you the way I learned it. So what you do is you point your fingers in the direction of the velocity vector, either or this way, it doesn't matter. Now, how you do, whether you do this way or this way depends on how your fingers have to bend. You curl your fingers towards B. So my fingers, the way they are right now, cannot curl towards B. I have to flip my hand over, and now they curl towards B. And it says that the force is downward. Does that make sense? I point my fingers towards V, curl them towards the magnetic field, my thumb points downward. And so the force is that way. So if you use your the one with the three fingers, your first finger is V, your second finger is, your middle finger is the magnetic field, and your thumb points in the direction of the force. So you just form your right-handed coordinate system. V points this way, the magnetic field points out of the board, and my thumb points down. Is that okay?
Yeah.
Okay. I gotta get a good magnet. So one of the problems I have with my magnets is that they're kind of messed up. Just give me a second. I have a bunch of magnets here. I gotta find which one is okay. Okay, I think this magnet's okay. All right, so I'm gonna demonstrate this for you guys. Okay, I'm gonna do it with this guy again. So let me remove the slide. Let me point to downward again. Okay, so we had, on the board, we had the particle moving to the right, and the magnetic field is out of the board. So I'm going to point the north pole of the magnet. That means the magnetic field is coming out of the board, or out towards you folks, okay? And so the force should be downward, okay? So let me try this. Does it move downward? Which way is the particle, which way is the object moving?
Up.
It's moving up. Oh, you sure?
Yeah.
It's moving up. Why is that? Why is it moving up, not down? By the way, to do this, I had to choose. These magnets are labeled north and south. And some of our magnets, after a while, the north is not north anymore. So I had to make sure I chose the right one. When I was eating lunch, I was using the wrong one. So why did it move up instead of down? What did I do wrong? What did I do wrong in applying this? Well, we got to think about, I guess I got to think about, oops. The particles. What kind of particles were being accelerated here?
Aren't they electrons?
They were electrons. So what can we say about the charge of the electron?
Oh, it's negative.
It's negative. So the right-hand rule only works for positively charged particles. It says that on the slide, right? The right-hand rule only works on positively charged particles. It doesn't work on negatively charged particles. And so if I have a negatively charged particle, then I have to flip my answer over. Does that make sense? If the charged particle is negative, and I apply the right-hand rule, I have to flip my thumb the other direction. So for a negatively charged particle, F is this way. And I don't want to say this, but I shouldn't say this, but I will. For an electron, you want to use the left hand. Okay, but we avoid the left-hand rule, okay? Because then it gets confusing. So all you got to do is for a negative charge, apply the right-hand rule and then flip the vector over. Does that make sense?
Yeah.
Okay. So again, let's compare the charged particle moving in a magnetic field and the charged particle moving, the electric field and the magnetic field. Let's compare them. If you have a charged particle in an electric field, it will experience a force even if the charge is not moving. The force will always be parallel or anti-parallel to the field. So if you have a positively charged particle, the force will be in the direction of the electric field. If you have a negatively charged particle, the direction of the force will be opposite to that of the electric field. Now, for a magnetic field, for a charged particle in a magnetic field, the charged particle must be moving in the magnetic field, and it must have a component of its velocity perpendicular to the magnetic field. And since the velocity vector is perpendicular to the force, then the direction of v constantly changes. Magnetic fields will not cause the magnitude of the velocity vector to change, but only the direction of the velocity vector. Oops. Okay? The magnetic field will only cause the direction of v to change. It's not going to cause v to change because the force is perpendicular to v. So it won't change the length of the vector, it only changes the direction of the vector. So what does that say about the work done by a magnetic force on a charged particle? If F is perpendicular to V, remember work, dW, let's do it this way. dW is F dot dr. And if we can write dr as V dt, if these two are perpendicular to each other, what's this dot product?
0.
0. So the magnetic field does no work on charged particles. All they do is they change the direction of the charged particle. They don't change the kinetic energy of the charged particle. Okay? And so the magnetic field is not going to change the kinetic energy of the charged particle. The electric field can change the kinetic energy of the charged particle, but not the magnetic field. This I can use. So let me show you I can use this simulation. So let me make this big. This is from MIT. These are free. This shows you a simulation of the motion of a charged particle in a magnetic field. What path is that?
It's kind of parabolic or
Yeah.
curved.
It's actually a circle.
Oh, yeah.
Okay, it's not letting me advance. Here we go. Let's look at the case where theta is 90. Let's look at the case where the angle between V and B is 90. I'll just say a couple more things and then I'll stop. So we have the magnitude of the magnetic force is Q V B sine of theta. That's from the definition of the cross product. And let's let theta be 90. So that means that S sub B.
We can't see the board, by the way.
Oh, sorry. Okay, I can't find my mouse now. Okay. Thank you. Okay, so that means that F sub B, if I plug in 90, is Q V B. And F is always perpendicular to V. And you've done problems like this in Physics 205 where F was always perpendicular to V. Okay. That's circular motion. Any system where F is always perpendicular to V is producing circular motion. Think of taking tying a rock to a string and whirling it around over your head in a circle. Isn't the tension in the string always perpendicular to the velocity vector?
Yeah.
So the motion is circular. And so this is the case of circular motion if theta is 90. Okay? And so really what we have now is, if theta is 90, we're making a charged particle going in a circle. So that means there's a centripetal acceleration. Okay? You have a centripetal acceleration. And so I'm not going to put I'm going to assume these are all magnitudes. QVB is mv squared over r. And then you can write r is QV, one second, QB over mv, or I'm sorry, I have it backwards. mv mv over qb. So for a given value of v and m, you have a specific value of r for the radius of the circle. So when you put a charged particle in the magnetic field, the particle will go in a circle. The force will be towards the center of the circle. And the radius is given by this expression. Notice that the m times v is momentum, right? And so magnetic fields can select the momentum of a particle. A particle with a different momentum will go in a circle of a different radius. And so magnetic fields can select the momentum of a charged particle. Okay. For a given P, there's a given R in a magnetic field. So sometimes you'll actually see them called these systems as momentum selectors, which will bend charged particles in a radius of a circle. Of course, sometimes they're called mass spectrometers. We'll talk about those later. Okay. But they are momentum selectors. So V is up, F is towards the center of the circle. Then which way is B then? Which way must the magnetic field be?
It's going towards the board if it's positive particles.
It's going towards the board, and
Yeah.
so it's like this.
Yeah.
So if you use the right-hand rule, oops, wait, hold on a second, I did that wrong. V cross B, yeah, you're right. So the magnetic field's into the board, and so we denote a magnetic field into the board like this. If the magnetic field was out of the board, we would denote it this way, a circle with a dot.
With a dot, yeah.
Okay, so we're going to use that notation because we got to think 3D now when we're doing magnetic fields. We're dealing with cross products, so you got to deal with 3D items. Okay, now we can write, since it's going in a circle, I don't know if you remember that V is R times omega, where omega is the angular velocity. And so if you do that, if you substitute R omega, then you get R equals M R omega over QB. And then you get a real simple relationship. Omega is QB over M. And so this will be the angular velocity of the charged particle in a magnetic field. Okay, so I think I'm going to stop here. By the way, if you wanted to figure out the relativistic corrections to these equations, they're not very complicated, but we just don't have time to do them. Okay, so next Tuesday I'll do a conceptual problem where we work with this equation, and look again, learning how to use the right-hand rule. So we'll do that next Tuesday, and I should easily be able to finish off the chapter next Tuesday and probably start the new chapter. In the meantime, just get ready for the exam. All right. I have office hours at 5 on Thursday, so I hope to see you there. So good luck on your studying. And remember, I gave you an extra day for the homework.